Alright, Assalamualaikum and very good afternoon. Boleh dengar?
Boleh.
Boleh. Alright. Okay, good. Alright, so today we will continue our lecture on pure bending. Okay, so this is the first time I'm using the synchronous mode of lecture. Okay, so why? Because this is the opportunity for you to ask any question. Okay, you can straight away ask any question that you think you are not really understand. So please, if you want to ask question, so please on your mic, okay, and then you can straight away ask me. Okay, no problem. Okay, during lecture, no problem. Alright, so please kalau ada soalan terus tanya. Yang ini saya tak nampak physically you, so tak ada segan sangat lah. Kalau dalam kelas tu you mungkin segan sikit. Okay, so sekarang you boleh straight away tanya, tak perlu malu, tak nampak. Alright, so let's continue our lecture. Okay, let me share the slide. Alright. Can you see my slide?
Yes, sir.
Oh, good. Alright, so we continue our lecture on pure bending. Alright, so I hope all of you already watched my first 3 videos. Okay, I already upload 3 videos in YouTube and also in Kalam. Okay, so video 1 basically is the fundamental concept in pure bending, and then in video 1 we have analyzed the stress and strain of the beam, made from homogeneous single material. Okay, so kita dah analyze beam, kita dah calculate stress and strain. Okay, stress and strain of the beam. Okay, dalam video 1 kita analyze beam yang diperbuat ataupun made from single material. Okay, single material. So kita panggil ataupun nama lain dia adalah homogeneous material beam. Okay. Alright. And then video 2 and video 3 I show you 2 example. Okay, so 1 example in each video. So I hope you already watched that one. Okay, so at least you get some idea lah macam mana kita nak solve the stress and strain for homogeneous beam. Alright, so today we will continue our lecture on composite beam. Okay, composite beam. So what is the composite beam? Composite beam adalah the beam that constructed, the beam that was made from 2 or more material. Okay, so video 1 kita analyze beam yang diperbuat daripada 1 material sahaja. Okay, so today punya lecture kita akan analyze beam, composite beam. Okay, composite beam. So composite beam tu maksudnya beam yang diperbuat daripada 2 ataupun lebih material. Okay, 2 material ataupun lebih lah. Alright. Okay. Alright. So before we start, let's do some revision. Okay. So this is the revision from the previous video. Okay. So let's say you have a beam. Okay. Let's say you have beam. Okay, homogeneous beam. This is a homogeneous. Okay, homogeneous beam. Okay, so one material. Okay, so the beam that is made from one material only. Okay, or single material. Okay, so and then let's say the beam is subjected to bending moment M. Okay, subjected to bending moment M. So what happen is, okay, when the beam is subjected to bending moment M, so the beam will deform. Okay, the beam will deform. Okay, and then due to the deformation, okay, so this is before deformation, this is after deformation. After deformation, so due to the deformation, the stress will be developed. Okay, stress will be developed. What type of stress? Normal stress. Okay, normal stress. Because we have two type of stress. So we have two type of stress. The first one is the shear stress. The second one is the normal stress. Okay, so the component or the member that's subjected to bending moment, okay, so the normal stress will be developed. Okay, so for this case, for the case of pure bending, the normal stress will be developed. Okay, so what is the relationship for normal stress? So normal stress due to bending is equal to okay, so the normal stress due to bending is given by my over I. Okay, my over I. So I is the moment of inertia. Okay, moment of inertia. Okay, or the sigma maximum is equal to the mc over I. Okay, semua dengar ke ni? Macam cakap seorang-seorang Dengar. Okey, tanya soalan sikit. Kalau tak nanti ingat cakap seorang-seorang tadi.
InsyaAllah.
Okay, alright. So what is the Y? Okay, what is the Y? So if we look at the side view of the beam, okay, let's say we do the sectioning of the beam. Okay, we do the sectioning, and then we see let's look from the side view. Okay, and then let's say the beam have rectangle cross section. Okay, let's say the beam have the rectangle cross section. Okay, so that is the side view. Side view of the beam. Side view of the beam. Okay, and then let's say this is the neutral axis. Okay, neutral axis. Okay, so I hope you understand. Neutral, I already explained in the first video. The neutral axis is passed through. It's passed through the centroid. Okay, the centroid of the cross section area. Okay, so let's say this is the centroid. So the neutral axis must pass through the centroid. Okay. Okay, and then let's say the question asks you to calculate what is the stress at point A. Okay, what is the stress at point A? So the stress is given by my over I. So for this case, if you want to calculate the stress at point A, so we write here YA. Okay, we write here YA and then sigma A lah, and then sigma A. Alright. So again. Alright. So what is the YA? Okay, now what is the YA? So YA is measured from the neutral axis to the point A. Okay, neutral axis to the point A. So that is the YA. Okay. So let's say the question asks you to calculate what is the stress at point B, for example, point B. So that will be the YB. Okay, that will be the YB. Okay, so from here, okay, from here and from the equation, sigma equal to my over I. Okay, so the sigma, the stress, okay, is increased when the y is increased. Okay, you can see here, if y increase, then sigma will increase. Okay, so what is the maximum value of y? Okay, what is the maximum value of y? So the maximum value of y occur at the top surface. So that is the maximum y, or bottom surface of the beam. Okay, this is also sigma max. Okay, sigma max. So we can write sigma max is equal to mc over I, because y max, okay, I can write here, y max. So y max basically equal to c. Okay, so c is measured from the neutral axis to the top surface. So that is the c. Okay, or from the neutral axis to the bottom surface. So that is a c. So for this case, y max is equal to c. So that's why we can rearrange the equation sigma equal to my over I into sigma max equal to mc over I. Okay, so the sigma max occur at the bottom surface or at the top surface. Okay, so where the y, okay, at sigma maximum, the y is equal to c. Okay, we can write yx now. So y max is equal to c. That's why we can write this equation. Okay, so sigma equal to this one. Okay, so sigma is equal to my over I. So this is what we call as a flexural formula. Okay, so sigma equal to my over I, we call this equation we call as a flexural formula. Okay, so bila saya cakap flexural formula, maksudnya sigma equal to my over I. Alright, so this is equation. Basically, this equation is derived assuming that the beam is made from homogeneous material. Okay, so again, this equation is derived with the assumption that the beam is made from homogeneous material. Okay, now what happen if we have the beam composite beam? Okay, what happens if we have the composite? How to calculate the stress and also the strain? Okay, so this is what we are going to learn today. Okay, so basically in this subchapter, we are going to calculate what is the stress and strain. Okay, what is the stress and strain for composite beam? Okay, for the composite beam. Okay, so let's start with the definition. What is the composite beam? Composite beam is the beam that is constructed by two or more different material. Okay, so for example, you have beam. Okay, for example, this is a steel. Okay, steel material, and then bonded with for example, aluminium. Okay, so firmly bonded by aluminium and then subjected to bending moment M. Okay, so this is what we call as a composite beam. Okay, so we have two material now, steel and also aluminium. So this is what we call as a composite beam. Alright, flexural formula was developed assuming the member is made from homogeneous material. Okay, this is what I explained before. Sigma equal to my over I. Okay, this is flexural formula, but this is only valid. This is only valid for homogeneous material or single material. Okay, So to apply a flexural formula for composite member, okay, so in order to apply this equation for the composite, okay, for the composite member or composite beam, we have to modify or transform the composite beam into equivalent single material beam. Okay, so what we have to do is, in order to apply the flexural formula, so we have to transform this type of this beam into equivalent single material beam. Okay, so we have to transform. Okay, transform composite beam into single beam, single material beam. Okay, and then so after that, only after that we can apply the flexural formula. Then we can apply the flexural formula. Okay, boleh ikut lah? Guys, okay lah?
Boleh.
Ke semua dah tidur ni?
Ada je. Ada, very.
Okay, alright. Cuba hadam. Tak tahu terus tanya. Okay. Alright. Okay. So what we have to do is, okay, so how to transform the composite material into homogeneous material. So we have to multiply, okay, we have to multiply the width of the material that intended to be transformed by the factor of n. Okay, this one I will explain later. Okay, so I will explain later in the next slide. Alright, so now let's see the stress and strain distribution for the composite beam. Okay, so this is the composite beam. Okay, so material 1, so this beam is made from material 1 and material 2. Okay, this is from the side view. Okay, so for example, you have beam, composite beam made from material 1 and also material 2, and then from the side view, okay, this is the front view. From the side view, okay, you can see this is the material 1. Okay, so I draw the side view. So this is the material 1 and this is material 2. Okay, so similar to this one. Okay, similar to this one. Okay, from here lah, yang ni. Okay, because the material 1 and material 2 is firmly bonded. Okay, material 1 dengan material 2 tu dia lekat ataupun firmly bonded together. Dia melekat ni lah, melekat. Okay, so once we apply the bending moment M, okay, bending moment M, so what happen, it will nicely, okay, let me draw here. So let's say you have composite beam, okay, and then subjected to bending moment M. So after deformation, so it will nicely deform. Okay, it will deform uniformly. Okay, so that is the M, that is the M. Okay, so it will deform uniformly. Okay, uniformly, so that, okay, because the deformation is uniform. Okay, deformation is uniform. Okay, so that's why the strain distribution, okay, the strain distribution will be uniform. Okay, so you can see here it is nicely distributed. Okay, the strain is nicely distributed. Okay, why? Because the deformation is uniform. Okay, so same thing, the strain, we can relate the strain with the deformation. So when the deformation is uniform, so the strain distribution also uniform. Alright. And then let's say okay, from the previous video, video 1, it had been shown that the strain is equal to y over rho. Okay, the strain equal to y over rho. This is what we have derived in the first video. So we have derived the strain equal to minus y over rho, and then based on the Hooke law, okay, from the Hooke law, the stress is equal to E1 strain. Okay, so if we replace the value of strain by y over rho, so you get, okay, sigma 1 is equal to E1 y1 over rho. Okay, y over rho. Okay, so same thing for stress of material 2. This one, stress for material 2 is equal to the E2 strain x. Okay, and then you can replace the strain equal to y over rho. Okay, so same thing here, sigma 2 is equal to E2 y over rho. Okay, y over rho. So rho is constant. Okay, so rho is the curvature. Curvature is constant. Okay, y is constant at the same location. Y is constant. So the different only E. Okay, so because the different material have different E, so you can see here. So what is the E? What is the E? So E is the slope. If you, let's say I draw the stress strain curve. Stress versus strain. Okay, stress strain curve from the tensile test. From the tensile test. So what is the E? E is the slope. Okay, so that is the E. Okay, so if we go back here, sigma 1, sigma stress for material 1 is equal to E1 times y over rho, and sigma 2 is equal to E2 y over rho. So the only difference here from sigma 1 and sigma 2, between sigma 1 and sigma 2, is the E, and E is the slope. Okay, E is the slope. That's why from here, for the material 1, you will have different slope. This is the slope for material 1. This is the slope for material 2. Okay, so this is E2, this is E1. So you can see different slope. Okay, different slope because the value of E for material 1 and material 2 is different. Okay, so the stress distribution is not as uniform as the strain. Okay, so this is quite difficult to apply. That's why we cannot straight. Okay, because we have two different slope, so that's why we cannot straight away apply the flexural formula my over I. Okay, so what we have to do is we have to convert from composite beam into homogeneous beam. Okay, we convert from composite to homogeneous beam so that the stress distribution will be uniform, and then we can apply the flexural formula. Okay, for example here, so you have composite beam, so this is the composite beam. Okay, so what you have to do is you transform into homogeneous beam. Okay, homogeneous beam, and then the stress distribution will be uniformly distributed. Okay, so the stress distribution will be uniform. Okay, so once you get uniform distribution of stress, so you can apply the flexural formula, which is sigma equal to my over I. Okay, but how to transform? Okay, so how to transform? Okay, let's say this is the material 1, this is material 2. Okay, so you can transform material 1 into material 2, or material 2 into material 1. Okay, so you can transform either one. Okay, 1 into 2 or 2 into 1. Okay, so let's say for this example, we transform material 2 into material 1. So what you have to do is you have to multiply the width, okay, lebar material 2 by factor of n, by n. Okay, so for example here, okay, material 2 have width of b. Okay, the width for the material 2 is b. So after transformation, bila you nak transform material 2 into 1, so you have to multiply lebar ni, b ni, by n. Okay, by value of n. Okay, but what is the n? So n is equal to the e over e. Okay, so let's say you transform 2 into 1, so you tulis 2, 1. Okay, so kalau you nak transform, this is for material 2 transform into material 1. If you want to transform material 1 into material 2, so n is equal to E1 over E2. Okay, so apa yang you perlu buat adalah you just darabkan dia punya lebar ni by n. Okay, and then we can analyze, we can assume that the material 2 already transformed into material 1. Alright, any question? Any question?
No sir, no sir.
No, clear? Clear or not clear? Alright, so this is the illustration. Okay, this is the illustration how we transform from composite beam, okay, composite beam into homogeneous beam. Okay, homogeneous beam. Okay, so for our case, let's say, okay, assuming that E2 is greater than E1. Okay, E2 is greater than 1. So this E is greater than E1. Okay. So after transformation, okay, so what we are going is we transform, okay, for this case, first case, let's say we transform material 2 into material 1. Okay. And material 2 is stronger, okay, than material 1. Okay, stronger means the value of E is greater than the others. Okay, the others. Okay, so what happened? You have to, okay, if you want to transform material 2 into 1, so what happened? You have to multiply by the factor of n. Okay, so for this case, the n is equal to E2 over E1. Okay, so since E2 is greater than E1, so the n will be greater or equal than 1. Okay, so that's why the width, okay, the width will become bigger. Okay, the area, you can see here, the area will become bigger after transformation. Okay, now we can analyze this beam, assuming that both are the same material. Material 1, this one will become material 1 after transformation, so we can assume this is also the material 1. Alright, now for second case, let's say we transform material 1 into material 2. Okay, we transform material 1 into material 2, and remember E2 is greater than E1, so okay, E2 is greater than E1. So after transformation, you can see that the area, okay, the area after transformation of material 1 become smaller. Okay, become smaller. Why? Because the n is equal to E1 over E2. Okay, this is material 1 transformed into material 2, and the n is less than 1. Okay, why less than 1? Because the E1 is less than E2. Okay, so this one. Okay, E1 is less than E2, so you get 0 point something. Okay, 0 something. So that's why the area after transformation will become smaller. Okay, become smaller. Alright. Okay, so this is the equation that I explained previously. So if you want to transform material 2 into material 1, so N equal to E2 over E1. If you want to transform material 1 into material 2, so N is equal to E1 over E2. Okay, 1 E2. Alright, so now let's say you transform material 2 into material 1. Okay, so let's say you have composite beam. Okay, so this is material 1 and this is material 2. Okay, so let's say you transform material 2 into material 1. So the stress, okay, so after transformation, okay, tukar. So after transformation, let's say it's become like this. Okay, so how to calculate the stress for this beam? So the stress for material 1 is equal to my over I, but the stress for material 2 is equal to my over I multiplied by n. Okay, if we transform material 2 into material 1, so you have to multiply the transformation factor in order to calculate the stress of material 2. Okay, so if you transform material 1 into 2, and then the stress for material 1 must be multiplied by n. Okay, so you kena darabkan n ni pada stress yang mana material dia has been transformed. Okay, has been transformed. Alright, so this is the explanation. Okay, if the area was not transformed, okay, kalau kita tak transform that material, then simply calculate the associated bending stress from the fracture model. Okay, so for the material that are not transformed, so the stress equal to my over I. Okay, so for the area was transformed, if the area was transformed, so for the material that has been transformed, the stress, okay, the stress is equal to n my over I. So you have another factor here lah, factor n. Okay, so you can you can apply the fracture formula, but you have to multiply by the factor n. Okay, transformation factor n. Alright, so we done on the theory. Any question? Tanya terus, tanya. Hello student. Any question?
No, sir, no.
Yes, m is moment. M is moment, not my. M is moment. Y is the distance. Okay, so ada orang yang tanya, yang my itu moment kan? M is moment. Y is the distance from neutral axis. Yang minus n tu perlu include ke? Okay, so alright, in some textbook, in the textbook, they write sigma equal to m y over I. So dia ada tanda negatif ni. Okay, so kawan you tanya nak letak negatif ke tak perlu? Alright, so kalau you tahu direction of deformation, tak perlu letak. Okay, tak perlu letak. Okay, so maksudnya let's say you ada beam. Okay, and then this beam is subjected to like this. This is the M. Okay, this is the M. Alright, so after deformation, okay, you will deform lah. You will deform. So kalau you do sectioning here, okay, do sectioning here. So because the beam is applied in this direction, so what happen is, okay, this is the bending moment, M. So that's the beam. That's the beam. This is the beam. Okay, so due to this moment, so what happened? This moment will pull in the material. Okay, and then the moment will pull out this material. Okay, so yang nampak ni dia berpusing. Satu arrow kat sini, satu arrow sini, baru dia berpusing. Okay, so what happened? Here will be in compression, and here will be in tension. Okay, this is the neutral axis. Okay, so the upper part will be in upper part of the beam will be in compression. The bottom part, the lower part will be the bottom part ataupun bawah neutral axis will be in tension. Okay, keluar tension lah. Macam belajar lah, keluar tension. Okay, kalau force masuk dia compression. So yang ni masuk compression, yang ni tension. Okay. So kalau you tahu tu tak perlu ada minus. Minus ni maksudnya kalau you letak minus pun boleh, tapi dalam buku tu dia assume kalau atas pada neutral axis y tu adalah negatif. Okay, sorry, y adalah positif. Okay, kalau dalam buku dia assume y tu adalah positif. Kalau dekat bawah ni y adalah negatif. Y negatif. So bila kalau you masuk balik dalam equation ni, y negatif dengan negatif, so you akan dapat tension lah. Okay, kalau you nak cari stress kat sini, so y adalah positif masuk dalam equation ni. So positif dengan negatif dia jadi negatif. So compression. Compression. Okay. Tapi kalau you tak nak guna negatif pun boleh, you tahu sendiri. Okay, you tahu sendiri stress equal to my over I. So you tengok y tu di mana? Belah atas ataupun bawah. Belah atas adalah compression, belah bawah adalah tension. So bila you dapat result, contohlah 200 megapascal. Okay, automatic you tahulah kalau y dekat atas, you terus tulis compression. Okay, tu kalau untuk direction macam ni lah. Okay, kalau kalau macam tu, okay, kalau macam tu, so yang atas akan jadi tension lah, yang bawah akan jadi compression. Okay, so boleh letak ataupun tak boleh letak bergantung pada nilai. Kalau you nak letak, you kena consider positive y or minus y. Kalau you tak nak letak pun boleh, tapi you kena tahu yang mana positif, yang mana negatif. Okay. Okay. Any other question? Okay, kalau tak ada, kita buat satu example lah. Okay, buat satu example. Okay, kita try one example. Two steel plate has been welded. Okay, so this is the steel plate, the blue one. Okay, the blue one. Okay, steel plate has been welded together to form a beam in the shape of T. Okay, to T shape. Okay, T shape. That has been strengthened by securely bolting to it the two timbers shown in the figure. And then you have a timber or wood lah. Okay, wood. Okay, you have wood. So this is this is the case of composite beam lah, because you have two materials, steel and also wood. Okay, so this is the composite beam. The modulus of elasticity is 12.5 for the wood and 200 gigapascal for the steel. So E for wood is 12.5 okay, gigapascal, and E for steel is equal to 200 gigapascal. Okay. Knowing that the bending moment M is equal to 50 kilonewton meter, determine the maximum stress in the wood, which is sigma max. Okay, sigma max for the wood. Okay, sigma max for the wood. So that is the question 1. And then question 2, the stress in the steel along the top edge. Okay, so what is the sigma for the steel? Okay, along the top edge, which is here, sigma here. Okay, so here, top surface. Okay, sigma for the top surface of edge. Okay, edge. All right. So now we have composite beam. Okay, we have a composite beam. Okay, so that's the wood and that's the steel. Then what we have to do is we have to transform. Okay, we have to transform the composite beam into homogeneous beam. Okay, we have to transform composite into homogeneous. Okay, homogeneous beam. Okay, so which one you want to transform? Steel to wood or wood to steel? Okay, either one. So normally I will transform from the stronger material into the weaker material. Okay, how do we know which one is stronger, which one is weaker? By looking at the Young modulus. Okay, because a steel have higher value of Young modulus, so I can say that the steel is stronger than wood. Okay, than the wood. So I will transform. Okay, for this case, I will transform steel into wood. Okay, into wood. Okay. Alright. So what you have to do is first we calculate the N transformation factor. Okay, transformation factor. N is equal to E steel over E wood. Okay, it's steel over E wood because we want to transform steel to the wood, so the steel will be at the top. Okay, and then over E wood. Okay, so E steel is equal to 200. Okay, over 12.5. Okay, using calculator, you will get equal to 16. Okay, so 16. Alright, so now, okay, let me draw again the composite beam. So this is the composite beam. Okay, and then the width here is 0.2. Okay, so I convert in meter, and here is 0.02. So we transform steel into wood. Okay, so what you have to do is you have multiply the width ataupun lebar steel ni dengan transformation factor N. Okay, so what you have to do is the steel, okay, the width of the steel must be multiplied by N. So here this distance, this one, become 0.2 times 16. Okay, same thing to here, because this is also steel. Okay, this is also steel, so the width become 0.02 multiplied by 16. Okay, how about the wood? How about the wood? So the width remain the same. Okay, the width for the wood remain the same, which is 0.075, and here also 0.075. Okay, so because we convert steel into wood, so steel punya panjang ni, lebar ni, you kena darab dengan 16. Yang sama juga, ini pun steel. Okay, ni pun still. Okay, yang ni. So you kena darab dengan 16. Okay. Now we can consider this is as this beam as a homogeneous beam. Okay, after transformation we can consider this is as a this is the homogeneous beam. Alright, so I hope you clear on this one. Okay, here is 0.3 and here is 0.02. Okay, so the height, okay, tinggi ni, the height is remain the same, remain the same. Alright. Okay, now we can apply for equation 1. You have to calculate the sigma maximum for the wood. Okay, for the wood, which is equal to the MC over I. Okay, because sigma max, so you replace Y by the C. Okay, so flexural formula sigma equal to MY over I, but for sigma max, okay, Y is equal to C, so you write C over I. Okay, that's why I have C here. Okay, so now first you have to calculate what is the I. Okay, what is the I? Before that, in order to calculate the I, you have to know where is the location of neutral axis. Okay, you have to know where is the location of neutral axis. Okay, for now we don't know where is the neutral axis. Okay, so as I mentioned, neutral axis located at the centroid. Okay, neutral axis is located at the centroid. So what we have to calculate now is the centroid. Okay, we have to calculate the centroid so that we know the location of neutral axis. Okay, so where is the centroid? Where is the location of centroid? So let's say the centroid is located at Y bar. Okay, Y bar. So Y bar is equal to the summation of Y A over summation of A. Okay, so this is from static. Okay, so I hope you still remember lah, sigma Y A over sigma A. Okay, so how to calculate? Okay, so okay, so the beam, so this one is equal to plus the top part. Okay, so I consider this is as a one shape, this is as a one shape, and then this is another shape. This is shape number 1, this is shape number 2. Okay, so this is shape number 1, this is shape number 2. Okay, so from this equation, so Y bar is equal to Y cacing. Okay, Y cacing. What is the Y cacing? So let's say here is the datum. So we assume this is the reference line. Okay, reference line or datum. Datum. So Y cacing for shape number 1 is, okay, so that's the middle for shape this one at the middle. Okay, so Y cacing is, okay, what is the Y? What is the Y? So here is equal to 0.3 over 2. Okay, so here is 0.3. From here to here is 0.3. So at the center of rectangle is 0.3 over 2. Okay, so 0.3 over 2. Okay, time area. Okay, area for shape 1, this one. So area equal to 0.3. Okay, time 0.47. Okay, so what is 47? 47 is 0.075 plus 0.02 times 16 plus 0.075. So you get 0.47. Okay, and then plus for shape number 2. Okay, the centroid is here. The centroid for shape number 2 is here, somewhere here. So from the datum, okay, from the datum, the distance is, this is y cachin. So the y cachin is equal to 0.3 plus 0.01. Okay, because this is 0.02, so the half is 0.01. Okay, and then the time area is 0.2 times 16 is 3.2. Okay, 0.2 times 16 is 3.2, so 3.2 times 0.02. Okay, and then divided by the summation of area, which is 0.3 times 0.47 plus 0.02 times 3.2. Okay, so y bar is equal to 0.2 mm. Sorry, 0.2 m. Okay, so solving this equation using calculator, you get y bar equal to 0.2 meter. Okay, so means that the neutral axis is located 0.2 from the reference line. Okay, 0.2. So that's the neutral axis and that's the centroid. Alright. You ada kelas ke lepas ni?
Tak ada, saya tak ada.
Tak ada. Boleh sambung?
Saya boleh je.
Tak seronok ah tengok slide je.
Boleh.
Boleh. Okay, alright. Good. Siapa tak boleh left je. Tak ada masalah. You pun mungkin you nak cuci baju ke, nak pergi apa tu? Cat rumah ke apa. So boleh left kalau nak left. Okay, raya haji pun dah dekat, so bolehlah buat persiapan. Alright, so we continue. So that's the location of neutral axis. So now once we know the neutral axis, okay, we can calculate the I. Okay, so the I is equal to the I1 plus I2. Okay, so what is the I1? I1 for shape 1, and then what is the I2? I2 is for shape 2. Okay, so this is for shape 1 and shape 2. Okay, so what is the equation for I? I equal to 1 over 12 BH power of 3 plus AD square. Okay, so that is for shape number 1 plus 1 over 12 BH power of 3 plus AD square for shape number 2. Okay, alright. Okay, so I draw again. So this is the shape number 1. And then plus shape number 2. That's the shape number 2. Then neutral axis. That's the neutral axis. Okay, and then neutral axis is located at 0.2 from the datum. Okay, from the datum. Okay, so for shape number 1, 1 over 12. What is the B? B equal to this one. That's a B. Okay, so for this case, B equal to 0.075 plus 0.075 plus 20 times 16. Okay, 20 times 16. Okay, tengok ni balik ah. Yang ni. So that is the B. Okay, so 0.05 plus 0.02 times 16 plus 0.075, okay, which is 0.47. Okay, 0.47, and then H, so that is the H. So H equal to 0.3, okay, yang ni 0.3, okay, power of 3 plus area is 0.47 times 0.3, and then D. What is the D? What is the D? Okay, so D is the centroid to the neutral axis. Okay, so D here, D, okay, D is the distance from neutral axis to centroid. Centroid. Okay, to the centroid. Centroid of simple shape. Okay. So for example, this one, shape number one. Okay, shape number one. For example, this is shape number one. Yang ni. Okay, yang ni. So the distance is, the height is 0.3. Okay, betul lah? 0.3 yang ni. So centroid untuk shape ni, okay, centroid untuk shape ni adalah di tengah-tengah dan jaraknya adalah 0.15. Okay, itu adalah centroid untuk shape ni. Okay, so yang kita cari tadi centroid ni centroid C ni adalah untuk keseluruhan, shape keseluruhan ni. Okay, so neutral axis, okay, neutral axis is located at the centroid. Okay, so which is 0.2 from the bottom surface. Okay, so if this is the bottom surface, so the neutral axis will be somewhere here. Here will be the neutral axis because here is 0.2. Okay, so because the top surface to the C, okay, the center of the simple shape is 0.15. So because the neutral axis is located 0.2 from the bottom, so the neutral axis will be slightly higher than the C. Okay, the C. Okay, so the D is measured from C to the neutral axis. Okay, ataupun neutral axis to the C lah. So that is the D. Okay, so for shape 1, okay, the D equal to 0.2 minus 0.15, which is equal to 0.05 square. Okay. Alright, so I hope you can follow lah. So that's the concept from static. So basically you dah belajar dalam static. Okay. You boleh refer balik dalam static. Tapi but this is very important lah. Okay. Important for your final. Alright. Okay, so this is for shape 1, and then we proceed for shape 2, plus 1 over 12. So what is the B? B is here. That's the B for shape 2, and that's the H. Okay, so B is equal to, okay, go back to this one. B equal to 0.2 times 16, so equal to 3.2. Alright, and then H. Okay, H is here. H is 0.02. Okay, 0.02 power of 3 plus area equal to 3.2 times 0.02 and H. D. Okay, what is the D? So D. Okay, let's say this is the centroid for shape 2. Okay, this is the centroid for shape 2, and then this is the D2. Okay, so what is the D2? D2 equal to from here to here, Buat apa ya? Okay, draw boleh ya. Okay, so that is the neutral axis. From here to here is 0.1. Okay, 0.1 because this is 0.2. Okay, the total height from here to here is 0.3 because this is 0.2. So here will be 0.1 from neutral axis to here. Okay, so 0.1. And then the centroid for shape number 2. Okay, the centroid for shape number 2 is 0.01. Okay, the distance from C to the bottom. Okay, bottom surface of shape 2. Okay, so from here D is equal to 0.1 plus 0.01. Okay, so equal to 0.11 square. Alright, so the I is equal to, okay, so you can using your calculator, okay, using calculator you can solve this equation. So I is equal to 2.186 times 10 minus 3 m power 4. Alright, okay, now we already have the value of I. So we can calculate the stress. We can straight away calculate the stress. Okay. 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 So stress maximum for the wood is equal to MC over I. So M is 50 exponent 3. So this is given in the equation. Okay, and then C is from the neutral axis to the top surface or bottom surface. Okay, so for this case we use the distance from neutral axis to the bottom surface because the distance is higher, 0.2. But this one from neutral axis to the top surface is 0.12. Okay, but from neutral axis to the bottom surface is 0.2. So we choose C equal to 0.2. Okay, so take the C with higher value. Okay, with higher value. So 0.2 over I equal to 2.186 times 10 minus 3. So it's equal to 4.57 megapascal. Okay, and then from the question 2 is sigma steel top surface, top surface. So sigma steel is equal to MC over I, but you have to multiply by N. Okay, you have to multiply by with N because we transform steel into wood. Okay, so we have to multiply by N. So this one N equal to 16. So M equal to 50 exponent 3. Okay, C equal to, what is the C? Okay, so go back to the question. Question is asking to calculate the top surface, stress at the top surface. So we have to take the distance from the neutral axis to the top surface. Okay, neutral axis to the top surface, which is equal to 0.12 over I. So I equal to 2.186 times 10 minus 3. So equal to 43.9 megapascal. So we finish. So that's all. So that is the stress of the wood, the maximum stress for the wood, and that is the stress for the steel. Okay. All right. So finish. Any question? Semua dah cuci baju ke?
Dah siap jemur tu.
Dah siap jemur? Okay. No. Alright. Okay, so open to any question.
Sir, ni ada rekod tak, sir? Masuk YouTube.
Saya rekod.
Alhamdulillah, okay.
Ya je clear. Lepas tu jawab exam tak boleh. Tanya. Tak ada soalan
Tak ada, so far tu je.
Okay, so kalau tak ada soalan, I think that's all for stress in pure bending. That's the subtopic for stress analysis in composite beam. Okay, composite beam. So I think that's all. Next class, I will give you another video for reinforced concrete beam. Okay, so thank you for your time. Okay, good luck. See you. Bye bye.
Thank you, sir.
Thank you.
Bye.
Thank you, sir.
All right.